Okay, so to drill home really the importance of which way you put the friction, let's do one last example about the inclined plane. So I'll call that example number 4. And we'll involve 2 masses this time. Okay, so we'll have example number 4. And we will not only have an inclined plane, but we'll add a pulley. So we have 2 masses, right? So let's call it M1, M2, like this. And let's draw the free body diagram. So let's draw the friction. So there is friction, especially for M2, not really for M1. It's just gonna be in free fall. But yeah, we can ask a couple of questions, right? So we can ask, for example, which way is it going? So do you think it's going to M2, let's focus on M2, is it going to move up the slope because M1's pulling it down? Or is M2 going to move down the slope? What do you think? Now, this really, again, depends. Well, if M1 is massless, let's take the extreme case. If M1 is basically a feather, M2 is not going to care about what this is doing, and M2 is just going to slide down, so it's going to move this way. So but if M1 is 1,000 tons, well, and M2 is too light, it's going to move this way. M2 is going to move up the slope. So it really depends on which way, which one wins. Again, but if they are the same mass, which one will go which way? Again, we really don't know. So we need to actually do it for both cases. So we'll draw all the forces we know first. Let's start with this guy. This guy's easy, right? So the force we know is there's a contact force, so there's tension, and there's a weight. And this guy, what are the contact forces? Well, there's a normal force, there is a tension over here, and there's a weight to it, right? So this is what's happening over here. But there's also potentially friction. And really, it depends on which way it goes. In fact, we'll set this up without friction first, because even without friction, the same problem arises. And you know what to do when you put in friction is just to see which way it goes and then have the friction oppose it, right? So actually, let's solve the even simpler case without friction, but still it has a question mark of which way does it go. Yeah, let's actually solve this. Let's see what happens. So the question is, which way does it accelerate, right? So we'll give the standard things. We'll give what the angle is, and we'll know what. So we'll know the angle. We'll know M1, M2, and we'll see what happens, right? There's a quick comment over here is I have duplicated my variable, so this should immediately come up as a red flag. The moment you see this in your exam, before you move forward to anything else, make sure you change that, okay? So this is, I'll put a W prime over here, and should I put a T prime over there? Now, normally you should, until you can convince yourself those are the same T. And since we have spent basically the whole of last lecture talking about why those 2 T's should be the same, remember, it's not because of Newton's third law, contrary to a lot of books might say, it's Newton's second law. It's because the rope is massless, right? So the left-hand side, MA, the massless, makes it 0. So the 2 T's will actually cancel out. Okay, so it's a combination of second law and third law that makes the 2 T's the same. So the W's are the same. This guy doesn't have normal force, so that is fine. All right, so we'll write down the Newton's law for each of them. So remember the 3 steps. We draw the free body diagram. We resolve the forces and write down Newton's second law. In fact, yeah, let's do this. So we've done this enough that we can just draw it here. And we've done it enough that this is theta. This is basically, I'll just skip right ahead. In an exam, do this properly. This is mg sine theta. And this is mg cosine theta. Okay, all right. So what's going to happen? Let's assume it's actually going this way, right? So I'm going to pick everything going along this direction as positive. So this is, I'm going to assume A is going this way and A is assuming this way and see what I get. All right. So on this side, on object 1, the free body diagram of M1 tells me MA equals to F net, right? And which M am I talking about? M1, which A1, and the net force on 1. And the net force on 1, with this way being positive, is W minus T. Okay, and now I immediately see a problem as well, that I have put M over here without caring which M it is. So that has to be M2. So be careful whenever you put something generic like this. G is fine. G is always a constant. Theta is also fine because there's only one theta in this whole problem, right? So make sure you distinguish what M. Don't just leave it as M. Otherwise, no one will know what that means, right? And this is M1G. So you can see the difference. This is M2G cosine theta. This is M1G. So don't put M over here. Otherwise, you might plug in the wrong numbers. Okay, so here we have M1G minus T M1A1. Okay, so for this guy, it's going this way. Let's look at this one first because it's easier. So we know that N has to equals to WY. Again, since AY or A2Y equals to 0. From Newton's first law, it's not going to accelerate up or down. So this will just cancel whatever that is. Okay, so so I can actually find what the normal force is because all of these should be given. So this would be no. How about WX? Sorry, the X direction over here. So we're gonna write MA equals F net, right, in the X direction, but also for the object number 2. So these two equations are from the free body diagram of 2. It tells me M2, A2, and F net 2 in the X direction. Okay. Now let's plug in the numbers. M2, right? It's just M2, and A2 is actually the same as A1 because if this accelerates this way, this accelerates this way, and if the rope is not going to loosen up or get tighter and tighter, then they have to accelerate with the same rate. Otherwise, if this is slower, then you're basically stretching it. If this is faster, then this will suddenly just catch up with this, which both of them is not true unless it's a spring. But if it's a rope that is inextensible, right? Inextensible massless ropes, it will always accelerate at the same rate. So this is actually one of the symbol, a special case. So until you can convince yourself the A's are the same, then make sure they're differentiated or distinguished until you can convince yourself, like I did, that they are the same. Now I'm calling this way positive this time, so we'll have T minus WX over there. That's W prime. Let me just make this prime so it's slightly more consistent. So the one without prime is here, and the one with prime is there, M2. Yeah, that's good. Okay, the T again, we have convinced ourselves we have a reason why these two are the same T's. So here we have now M1G cosine, sine theta, and should I have M1 or M2? M2, there we go, M2, M2A. All right, so now you're faced with, so here you have calculated N, there's nothing more insightful I can do over here. Now I have this equation here and this equation here, right? What am I curious about? I'm curious about A. So what am I given? I'm given G, M1, M1. I know all those. I know M2, I know G, I know theta. I don't know A and T. So two equations, two unknowns. Again, you've got to do what you got to do. It's minus T, it's plus T. Just add them together. These will cancel out. So if I add left-hand side, I have M1 plus M2A. And we add the right-hand side, the T's will cancel. So that will have M1 G, the T's will cancel plus this, so minus M2G sine theta, right? So what am I curious about? I'm curious about A, so we can isolate that and make that the subject. So I have, let's pull out the G, and I have, right, so I have a common factor of G over here. I have M1 minus M2 sine theta over M1 plus M2. Okay. That is the acceleration if it accelerates that way. Okay, Again, do some quick sanity checks. Let's see if M2 is 0. We can do both. We can assume M1 is 0 and M2 is 0, right? What will happen? Let's see if M2 is 0, I expect what happens. I expect this to be completely negligible, and this would just be in free fall, right? Let's see what happens. If M2 is 0, right? So you don't have this. If M2 is 0, what do you get? Well, you just have M1 over M1. So that's just 1. So you have A equals to G. So the acceleration of the whole system, if that's 0, is just G. So it makes perfect sense, right? What if M1 is 0, right? Let's answer that in a second. But let's also, well, if M1 is 0, the reason why we should answer that in a second is because we should first think about if M1 is 0, it will probably go this way. Now, should I redo the whole thing? What do you think? Because now it's going the other way. Should I redo the whole analysis? Is that, in other words, is that equation valid for going the other way around? Now ask yourself, that equation, the conclusion we got, what is that? That's a consequence of me dealing with these 3 equations, right? This is the free body diagram of 2. This is the free body diagram of 1, of 2. So this is a conclusion of the free body diagrams. Now, is the question, my question of, is this valid? Is this valid if A goes the other way? Right? In other words, if this is somehow larger than this, because the moment I put M1 equals 0, right? If I put M1 equals 0, I will get a negative number. So in other words, right? In other words, is this valid if A is negative? So I said this is a conclusion of the Newton's second law, which is a conclusion of the free body diagrams. So is this equation valid means, is the free body diagram valid if A is going the other way? Ask yourself, the forces. Let's start with the easy one, right? If you have something complicated and something easy, which one do you want to start with? Start with the easy one. So if it's going this way, is this the same 2 forces acting on it? Or is there something new? Or something should change? No, those are the same forces. It's going this way. Is there anything new without friction? No. It is exactly the same case. When you will same have the normal force without friction, right? Same weight, right? Same tension. So the free body diagram is exactly the same. So this formula is exactly the same. So this is valid. The domain of validity applies to it going both ways, right? So now let's actually check once we're convinced of that. So this is how we analyze things as a physicist or as a scientist, right? We ask the questions very precisely. And if that is 0, right? Let's do a final check. If M1 is 0, so that goes away. What do we have? Well, we have M2 over M2, which again cancels, and we have minus G. So A is minus G sine theta. Do we recognize that? Almost up to the minus sign, right? If it's G sine theta, we recognize that is the acceleration down a slope. Back to problem number 1, inclined plane problem number 1. Where does the minus come from? I think you can answer that as well, because we call that positive. So minus A just means it's going this way, and it's going down this way. So the magnitude is G sine theta. The direction is negative of what I called positive. Right? It's basically, if I want to describe that in words, I would go like the magnitude is that, and it's down the slope. The direction is down the slope. Okay, so we'll just put the negative sign here just so it's like more consistent over there. But that is the analysis. All right. Now, what's different is if you do add friction, now you realize, and this is my challenge for you, right? The question is, how will this change? What is A if there is kinetic friction on M2 over here? And this time you will ask yourself, if it goes this way, is the free body diagram the same as if it goes this way? And the answer should be no. So you will produce 2 answers. If it is going this way, what is A like? If that is that way, what is A like? All right. And you can put your answers either in the comments below or in Piazza, either way you like. And you can have your friends confirm or deny your workings and test your understanding. So this is like the ultimate Pulley plus inclined plane problem. If you can do this, you have a good grasp and you can do any inclined plane problems. And just to add a quick footnote to that as well, this is a good point to review the textbook example, chapter 5.6 and 5.7. It's a good complement to look at this problem together with those two examples as well.